Hello! In this last and final lesson, we will be taking and applying everything we've been learning about quadratic functions to the idea of motion. So in this lesson, we'll look at three equations. One that takes distance and calculates it from both the time and the acceleration due to gravity. The next formula we'll look at adds this concept of distance some value for an initial velocity. And lastly, we'll look at a function for height, which builds on that form. We're just using initial height along with the initial velocity, gravity, and time. So these three equations you'll have a pretty good grasp of by the end of this lesson. So to develop the first equation, let's talk about the concept of acceleration. Acceleration can be derived from the proportionality for velocity. So we can write velocity is directly proportional to time using our proportionality function. Remember, if we were to do a over t, that's an inverse proportionality, so we don't want that. So to find out this proportionality, let's take an example of something falling. Say something accelerates to a velocity of 96 feet per second in 3 seconds. We can use that information in our proportionality to calculate the acceleration. So, for something falling due to gravity, the acceleration will be 32 feet per second squared. So we could write the velocity is 32 times time, where the units of this equation, or units of measure, would be in feet per second. And for 32, that's feet per second squared. That's how we measure acceleration. Times second. So note the units on the right side. If we have feet per second times second, that means one of the seconds cancels and gives us a result in feet per second. So with units of measure, the two sides of the equation will always equal out. So if we talk about something falling then, or we'll call it free fall, we use the variable g to denote the acceleration due to gravity. This is actually an important variable we'll continue to use. G is 32 feet per second, or in meters, 9.8 meters per second squared. So these are units of gravity on Earth. We could talk about acceleration in different contexts, say on a different planet, where the acceleration due to gravity is different. But for this problem, we'll use 32 feet per second if we're using feet, or 9.8 meters per second squared if we're using meters. So if acceleration can be derived from the fact that velocity is directly proportional to time, we can then apply that to the concept of the distance something travels. Since it's directly proportional to time squared, we can write this also as a proportionality. D equals AT squared. So again, we can find this constant proportionality by looking at example of something falling. So we measure it falls 576 feet in 6 seconds. We can use that to calculate the constant of proportionality in this case. I'm zipping through this kind of fast. You can always pause these videos if you want, but I'm going to keep moving. So since we know gravity is 32 feet per second, the constant of proportionality in this case, A, is 1/2 g. So we can write distance as 1/2 gt squared, where the units of measure in this case are in feet. And if we write gravity as feet per second squared, time squared lets us cancel our seconds, so the units are consistent here. So let's see how this equation can be used to answer this question, how long it takes something to fall a specific distance, say from the top of the mods. If we look at our formula, we know the distance is 35 feet, so we're looking at how long it takes something to fall that distance, t. So, by plugging into this formula and solving, this gives us 1.48 seconds. So you can see how this formula can be used to answer simple questions of how long it takes something to fall. But we're going to add on to this formula now. If this formula can be used to find something that's accelerating from rest, what about something that's already moving? I think we've already studied this. We know that distance is directly proportional to time if we have a constant velocity, so we're going to use v naught to describe that constant of proportionality. And so if we have that initial velocity v naught and something accelerates, the total distance traveled is the sum of the two. And finally, so this is our new formula. We can look at the units of measure to see that they're consistent. You can take the time to look at this if you are curious. But basically, what we got is a new formula that can be used to answer questions such as how do you find out how high something goes if you throw it up or shoot it at a specific velocity. So for this example, if we shoot a bullet up at 80 meters per second into the air, how high does the bullet go? We can find this by considering the fact that our velocity, we have to get our bearings on this problem. If our velocity is 80 meters per second up, gravity then would be a force acting down, or an acceleration downwards. So since we have meters in this problem, we're going to use negative 9.8 meters per second. So if we plug all these numbers into our equation, this gives us the equation of a parabola that's facing downwards. So to find the maximum height, how high this bullet goes, that's like finding the vertex of this parabola. So to find the vertex, we first need to find h, and we've done this before, so you can check my work on this. So once we find h, that's how long it takes to get to that maximum point. Now we can find k by plugging that back into our original equation. And solving this gives us a height of 3,265 meters. So go ahead and check me on this. See if this makes sense. So that's our formula for distance in its most general form that we'll be using. But we're going to generalize this even a little further to talk about the concept of height. So we're going to take this formula, instead of distance, we're going to talk about height and add this term h naught for the initial height. So in general, we'll talk about h being up, a height above the ground or height above some reference point, and then the acceleration would be gravity, and since gravity is acting downwards, it's a downward acceleration, we can rewrite this formula as follows. So this is the final formula that we'll use. I'm working out the units of measure here, so you can see that they all do cancel. In this case we're looking at meters, but you can see that all the units for each term ends up being a measure of meters. So this equation makes sense. Let's apply it to the idea of throwing something. Say a football. We throw it up at 40 feet per second. If we're already standing 6 feet above the ground, how long does it take this ball to then reach the ground again? So we'll use this formula, plugging in, Alright, so we're going to plug in all these values from our problem. 6 feet for the height, 40 feet for the initial velocity, 32 feet per second, squared for the force of gravity. So that gives us a parabola of this form. So if we're trying to find out when this ball hits the ground, that's when the distance, or excuse me, I gotta fix some things. We're talking about height in this case. So we're going to use h. And so when that height then returns to the ground, that's when h is equal to 0. So that's like solving this formula for 0. Finding the x-intercepts, which we know how to do using our quadratic formula. So, another opportunity for you to practice and check my work. But if we solve this, we get something like this that has two solutions. One is a negative result and another is a positive. The negative result would be back in time, so we're not really going to consider that one. We'll look at the example, or the solution in which 2 seconds from now, in 2.64 seconds, according to our model, this ball will reach the ground. So now you've seen these three equations and have a little grounding for how to use them. Good luck applying them on the exercises.